the rate of change was, how functions were moving, were they increasing or decreasing, and then we use parabolas to see that point of change that they might have, and when the function might be becoming different. And we're going to continue to look at this behavior. The core concept of the line is still underneath it all. When is it increasing or decreasing? That's really what the line gave us. Then in the parabola, or the quadratic equations, give us our turning point with the vertex. Any higher polynomial can be made up of chunks of different of those things. And those chunks come from multiplication. And so notice we're going to look at how can we divide polynomials, because we want to break them apart. And so we did this early on with the idea of factoring. So if and I'm going to show this. If I know I cross the x-axis at 4 and -2. I don't know the rest of the shape of my polynomial or my quadratic right now, but I know I cross at -2 and 4. Well, crossing the x-axis meant that f of x equals 0. So what happens here is I have something where if I put in -2 for x, I get 0. And if I put in 4 for x, I get 0. So I have x plus 2 equals 0. Well, what happens if I put in -2 for x? I get 0. So where did this come from? Oh, wait. These are my x values. So I could say x equals -2 and x equals 4. And if we notice, this is where I end when I solved a parabola. This was my end point. So we're going backwards. We're going to reverse this process. So I'm going to put all of my numbers on one side, so I add 2 to each side. And I get x plus 2 and x minus 4. And if I have some relationship that are connecting these 2 points, something had to happen that they were together. Right now I've got 2 solutions. Now, in doing quadratics, we said, hey, these could be factors. We factored these out, or we used the quadratic equation. We did something to get through them. So if they're factors, we're relying on the idea that A times B equals 0. So if this is my A and this is my B, well, that equals 0, and that equals 0. 0 times 0 will give me 0. So I'll put my 2 factors together, and I'll FOIL. And this was the function that defines this. Now, depending on where other points of data are, I have some coefficient out front that determines my A value, but I have the base polynomial. So that's going from our answers to our polynomial. We spent time learning how to factor this down into these terms. We want to be able to do the same thing now if x is cubed, x is to the 4th, and x is to the 5th. Because putting these things together is a multiplication, this factoring will rely on divisions. And so that's why we're going to talk about dividing polynomials. We're going to look at the mathematical operation of dividing polynomials. We're going to look at different methods for doing it, and then we're going to look at how we can find what we need to divide by for our polynomials. So we're going to start just dividing. We're going to divide, we're going to be given what to divide by, we're going to get simpler and simpler terms from it. Eventually, we're going to have a polynomial of any degree, and we're going to have to figure out what we need to divide by to get our answers or solutions. So we're using all the little bits and pieces we used with a line, with a quadratic, and we're going to put it all together for any degree. And I've warned you, and many times when we looked at something on the board, I would say, hey, we're going to do this for any degree. We're going to be able to break them down into these littler things, smaller parts, component parts. And so we're going to talk about the division here. Now we will only get through probably the first 2-3 sections of this. We're going to do synthetic division at the last half of the week, and the remainder theorem, definitely all in one class on its own. The remainder theorem leads into our finding rational roots, and it's the key. But first, we're going to learn to divide polynomials. And so we want to divide a polynomial by a monomial. So I'm going to take this here, and I'm going to do it on the blackboard. I find the slide versions of these are not as enjoyable as my babbling. No, I'm going to look at the component parts. So let me write this here. I have 6x cubed minus 3x squared plus 2. And that is all over 2x squared. All right, let's switch over here. So I have rewritten this here, 6x cubed minus 3x squared plus 2. If we kind of reverse the idea of what happened when we had a common denominator. So I'm going to think in blue. Well, I'll think in green. If I had A over B plus C over B, I could write everything as a common denominator. These individual terms came from the two numerators. This is why we focused a lot on getting common denominators. I'd say early on when we were looking at the properties of real numbers, I should have shown a proof on how this comes from. So I know in my developmental math class and in my 097 we look at how this works from the property of real numbers. But once we have a common denominator, we can bring the numerators across. Well, this is saying I have a common denominator and I have these linked numerators. In fact, I have terms that aren't like each other. So I can reverse this process. I could say, hey, this term, let's see, I'll make that the yellow term. I'll make this the green term, and I'll make the 2 the purple term. And so the yellow term was its own thing. And the green term was its own thing. And the purple term was its own thing. If I want to go forward, these all have the same common denominator. I can use my rule of common denominator in fractions to blend these together, and I would get this. But I'm dividing. I want to go backwards. I want to simplify this. So notice this term is a monomial. What I am dividing by has no additions or subtractions in it. Oh, is the audio looping? Okay. What is happening here? All right. All right, so we got an audio glitch. You hear silence now. Can you hear me now? Yeah, I was quiet while I was typing. All right, can we have an audio check? Yep, okay. And you should hear me talk shortly, Jim. There's about a 20-30 second delay. And if you came into the stream a little late, you might be on a longer delay. All right, good. All right. Yay, audio check. Sorry about that. It happens sometimes, and sometimes there might be a local echo coming through. What I'm going to do here, okay, come back to my graph. Okay. Woohoo! Thanks. We can treat each of these terms the same. Or the same as independent beings, I guess would be the better way of talking about it. So here, 6 divided by 2 is 3. Then x cubed divided by x squared is x. I'm simplifying each fractional term on its own. 3 divided by 2 is 3 halves. Right? X squared over x squared is 1, so I'm left with an x half, 3 halves on its own. 2 divided by 2 is 1. And I'm left with x squared down below. And that is the answer to my division. When the downstairs is a monomial, I break it into its individual terms. At another monomial here before going on to a non-monomial. Dividing by monomials. Let's get another one. Scroll down. So if my function, if I'm looking at division of 3x to the 4th minus 2x squared minus 1 divided by the monomial 3x cubed. Yeah, that static noise in the background is the tea kettle. As I am right off of the kitchen here, and we have the family working their way out towards their day. So someone has put the tea kettle on. So the static you're hearing is the tea kettle going through. Yes, there will be some background noise. Occasionally you'll hear the squeaky door that I need to oil. All right, so we're dividing by a monomial, so we can break it apart into individual terms. Again, the key is there are no additions and subtractions in the denominator. So I can look at it term by term of the numerator, sharing that denominator. When learning new things like this, where it's a deconstruction from a rule, always double check that you could go back. That, hey, I have a common denominator, so I can blend the numerators. And if I take 3x to the fourth minus 2x squared minus 1, do I get back up there? And I do. A lot of our mathematical properties are reversible. The ability to distribute can be reversed. In fact, we're kind of doing that reverse distribution here. This division is taking out something that would have been distributed into one of our terms. So, 3's cancel, and the x cubed leaves me 1x upstairs. This gives me 2/3 out front. The x squared is going to cancel all but one of these downstairs. And this one is as easy as it gets. Okay? Nothing more I can do there. If I wanted to check myself, I could multiply this whole thing by 6x cubed, or 3x cubed. Sorry, 3x cubed. And if I were to distribute that to each term here, I would work my way back up. And so it is a reversible process. Division is the reverse of multiplication. And our ability to divide by a monomial is able to work us backwards and forwards, which will be nice when we get things like this. All of these have a common factor of 3x, so I can divide by 3x. Right? Divide this by 3x. Whoops. Divide by 3x, showing you the why we start our divisions. And so this would give me x squared plus x plus 1. Well, that 3x would have been one factor, so I'm going to rewrite this equation as 3x times x squared plus x plus 1. And I now have the ability to say, hey, 3x equals 0. That's one of my solutions. And x squared plus x plus 1 equals 0. That'll give me my other solutions. That's where this is all going, is that we can take these larger polynomials and break them down. If our last term in the polynomial still has x in it and we don't have a constant, we're going to be able to pull at least a monomial out. Because I have at least whatever that last term is working its way through. And so that's the thing to look for. If this was 3x cubed plus 3x squared plus 3x plus 5, I couldn't do this. I wouldn't get a nice clean term out on the end. And that's going to be part of our job, is determining when we can't do it. And so monomials are what lets us do the greatest common factor. All right. Well, I can divide by monomials. Well, I can also divide by another polynomial. And here, when we're going to look at dividing by polynomials, we're going to borrow an idea from long division, and we're going to start doing long division. So I'm going to grab our polynomial out here, and we're going to come back up to the blackboard here. First thing I want to look at is I need to save this. I ran out of blackboard space. Close this. Reopen it as blank. I'm trying to get a key shortcut that will do all of these steps for me. I haven't written the script for it yet. Sorry about that. Alright, so I'm going to borrow the idea from long division. So if I take 2,600, or 26,100, and divide it by 36. Without using a calculator, and the algorithm we're looking for here is really dependent on not having the numerical answer, but having a process. And so this becomes the value that we want to divide by. We're actually dividing by the 30s, right? Each one has a place value. And so we look at each place value here, and we work in descending place, order of descending place values. And so we take our number and we say, hey, can I divide that into my 20,000s place? Well, 36 does not divide into 2 evenly. So we tend not to write a 0 up above, but we just move over. And we look at 36 and we say, hey, can you divide into 26 evenly? And you can't. And so we get over to the hundreds place and we go, well, hey, 36 goes into 261. Well, how many times does it go into it? 8. So 7 times, I believe. 7 times 6 is 2. Carry my 4. Right. So this goes in 7 times. I am on the blackboard and it didn't switch over. I was erasing the blackboard, and when it erased, it switched you back to the other screen. Let me restart here. Thank you for that, Leica. Oops, there we go. All right, so I will repeat on the blackboard. Thank you for that heads up. And just to double check, I'm looking at my stream now. Yes, the blackboard is showing. Okay. All right, so the algorithm we're going to look at is the algorithm of long division, and it's dependent on place values. And so we're taking 36, and we're seeing if it can divide into each individual place value. So 36 can't divide into the 10,000s place because 36 does not divide into 2 as a whole integer. 36 also does not divide into 26, but it does divide into 261 7 times. So proceed our way over until we find the first place that this divides into. We put the number of times it divides into, and we multiply that back out. So 2, here are your 4, 7 times 3 is 21, so 25. And we subtract. 2 gives me 9, and so I have 9 left over. I bring down the 0 because I am now moving into my next place. I'm moving into the tens place, and 36 goes into that twice. So 2 times 6 is 12. Now notice I am focusing on my new number. This algorithm starts with up here. once I get the subtraction, my new number that I'm looking at, that I'm now doing my division with, is here. And so 2 times 36 is 72. I subtract. So I get 8 and 1. I bring down my 0. And 36 goes in that 5 times. 5 times 6 is 0. Carry my 3. And I have a remainder of 0. And so 2,600, or 26,100 divided by 36 is equal to 725. Now I've got it. We can do this on a calculator. That's fine. But the algorithm of focusing on place values and subtracting out to get the next number we work on is what's going to be borrowed very, very heavily in polynomial division. And we can treat the different variables of x as if they are place values. So the division I want to do here is going to be a polynomial, and we're going to borrow this algorithm from numerics. So I have 2x cubed minus 3x squared minus 11x plus 7, and I'm going to divide all of that by x minus 3. Now the idea we're going to borrow is that each of these terms is a place value. The individual degree of the variables are the place values. So I'm going to rewrite this in the form of a long division. I'm going to be dividing by x minus 3, and I'll put my division bar out here. So we want to see how many times this goes into each of these by place value. So our focus will be, we start with our leading terms. So this is my leading term here, and this is my leading term here. So I want to know how many times 2x cubed is divided by x. I look at just my leading terms. So step 1, look at leading terms. And if I do this division, this isn't as bad as numbers. I don't have to guess my way up. I can, if this x is going to cancel this, this will give me 2x squared. So this part, this leading term, goes in 2x squared times. So I'll write up here 2x squared. So I divide leading terms. I'm just going to put LD for leading terms, and we'll write it above. Notice I'm lining up my x squared with my x squared. I'm treating the degree of each term as its place value. And I have 3, 2, 1, and 0 for my x's. Now I multiply. I'm going to jump up a board here. Okay. When I had the 7, I multiplied it by 36 to get the 252. So here, I'm going to take the 2x squared, and I'm going to multiply it by the x minus 3. So 2x squared times x minus 3. So the 2x squared comes to the first point. I get 2x cubed minus 6x squared. Well, that's what I want to write here. I get 2x cubed minus 6x squared. If I have done, and so we'll say write this below. And I write it below, lining up the powers of x. Right? Now my cubes are cubed. Now if I did this right, always, if I do this first leading term, whatever I multiply should be exactly the same on that first term. And so we subtract. Again, I'm going to scroll up a board here. If we were in class, I'd be pointing from the left board to the middle board. I subtracted these two things to get the 9. So when I subtract these, well, I'm going to show my subtraction by changing my signs. Okay? So when we subtract, we change signs. 2x cubed minus 2x cubed is 0. These will always cancel out. If I did this right, I get the same thing, and they cancel out. These terms, 6x squared and minus 3x, gives me 3x squared. Let me go back, change color, back to where I was, sorry. And so pull down next term and repeat. This is a repetitive process. As these 8 steps go over, you look at the leading terms, you divide the leading terms, you write it above on the bar here, sorry. You multiply, you write the result of your multiplication here, you subtract. And now I pull down my next term, and I have a new leading term. And so now I'm ready to repeat with this being my starting point. So I'm going to break down these rules here, and then we're going to go through this step by step. But this is what it borrows from long division with numbers. We are doing it now with variables, and we're letting the variable power hold individual places. So let me change coloration here. So our rules: divide leading terms. Write the answer. Yes, Jen, I will scroll back up in a second. I'm going to write this down and then come back. I'm kind of summarizing what's up above. Write the answer above. Multiply the answer by the divisor. Write this result below. Subtract. Pull down next term. And repeat. And the note I'm going to put on this is always line up powers of x. So this is the algorithm here. I'm going to leave this up for a minute, and then I'm going to go back up to the other problem and we'll just keep running through these steps and repeating through them. We're gonna look at this with when we have a remainder and when we don't have a remainder, and where different divisions come out. All right, and so we will have a remainder here, and then we'll check some others. Make sure you have these referenced somewhere. I'm going to keep talking about these. See this, whereas in class I'd keep looking at your pencils to see if you're still writing or not. But for here, I'll just watch the clock tick a little bit. Alright, so I'm going to continue doing that on this. But I'm going to get my eraser out and erase these things off on the side here. My eraser is a true eraser, but I can fix this in a second. Oh, maybe not. I'll fix this in a second. You guys bear with me here. Okay, this happens in class all the time where I'm stuck on the blackboard. There we go. That's a better eraser. That's the eraser I wanted. Actually, it looks like my eraser in class. There we go. All right. Yes, cats do want to learn too. I think they learn better than us. All right, so I have done my first step here. I looked at my leading terms, which was the 2x cubed and the x. I divided them and I got 2x squared. I put that up above and I multiplied, which gave me 2x cubed minus 6x, which I put here. And I subtracted. Now I repeat. This is my new leading term. So I'm going to not do the leading terms off on the side. I'm going to look at this. I'm doing 3x squared divided by x. Well, 3 is positive, so that's going to give me a positive 3, because 3 divided by 1 is 3. And x squared divided by x is x. Right? So let's remultiply 3x times, yes, I get the same thing. Now my next step is to multiply. So I'm going to take 3x times x minus 3. And I'll do it term by term. So 3x times x is 3x squared. 3x times negative 3 is negative 9x. Now again, if I did this right, and I'm saying that not as, oh no, we're going to do this wrong, right? It's a place we double check. These first terms should be exactly the same. This algorithm makes sure these first terms are the same. So my next step is to subtract. So when I subtract, I change my signs, which turns this into an addition. These will cancel out. And negative 11x and 9x gives me negative 2x. I bring down my next term, positive 7, and I repeat. So I'm going to do a quick jump down here. All right, I divided my leading terms. I wrote the answer above. I multiplied. I wrote this result below. I subtracted. I pulled down the next term, and I repeated. I looked at my new leading term. I wrote the answer above. I multiplied. I wrote the result below. I subtracted. I pulled down my next term, and that's where I'm at right now. So I've pulled down the 7. And so my new leading term is negative 2x. And so negative 2x divided by x. Well, the negative 2 is going to stay, right? The negative 2 is going to stay because negative 2x over x, the x's cancel. So I'm left with just the lowly negative 2. Now I'm going to multiply. Negative 2x times x is negative 2x. And negative 2 times negative 3 is positive 6. And I'm going to subtract. Again, if I've done this right, these two first terms should be the same. And so I'll change my signs. And that leaves me with, whoops. A remainder of 1. Now, remainders are neat things in dividing up polynomials because it's saying underneath it all, I can say this is my answer with a remainder of 1. And remainders, we can also write it as 1 over whatever we had here. And so you'll find I will tend to write them like this unless I need the remainder. For a lot of what we're going to do first, we're going to write these answers with a remainder out to the side, because we'll be dealing with something called the remainder theorem coming up. I'm not sure I'm going to reply to that last comment, just to say that the answer is that's probably truth for everything. It is easier. Anyway, I'll leave it as that. All right, so this is most of today's talk. We've got about 20 minutes left. What I'll do here is we'll start back up with dividing polynomials. Dividing polynomials, we're going to look at loads of different variations we can see on these. What I wanted to focus on was the algorithm is the same as the long division algorithm. I do find that modern tendency in school to use calculators, a lot of people don't have the long division algorithm down. So I want to really focus on these rules. We divide the leading terms, write the answer above, multiply the answer back out by the divisor, and what we get from that, we write down below, we subtract, pull down the next term, and repeat. And we repeat until we're down, we've cleared the ones place. Always line up the powers of x. And I'll start off next time with where that gets weird, where like what happens if you have x cubed minus x, but you're missing the x squared? What should you do with that? And other different things to go through. So I'll plug that all up. All right. Any questions on any of this? I will fix the audio on the videos I have there. I'll put some subdivisions on it. I hope you saw the note. I'm recording 4 lectures during the week. There are 2 lectures of material, Tuesdays and Thursdays. I recorded Tuesday and Thursday, and then I also record those 2 things again Thursday evenings. That's so schedules have changed, right? People's watching cats, watching children are different than what they were not having face-to-face meetings. And so because of that, I'm not requiring people to be in during class time. But having questions helps. It helps me adjust things, especially having questions on the material. Questions on the recording type stuff, the switching back and forth on screens, I don't do when I record the stuff on my own. I actually can watch what I'm doing. It's a little bit easier. But please ask questions on the material. Please send me email on the material. What I'm doing today, because questions have come up on the stuff for Chapter 3, is I'm recording examples of all the word problems. I'm going to have those up that are on the practice exam. Again, I know there's been problems with Pearson, so I'll modify the due dates. And sorry, with Jen saying with how long she is working, You're not required to be here for a live lecture. I'm not doing attendance. I will post the links to the lectures. You can watch them at your leisure if you can't make a given time. But if you want to be here and interact, that's wonderful too. So I'm recording the word problems from the Chapter 3 practice exam. We're looking at taking the online exam by the end of the week, but I'm going to continue talking about Chapter 4. All the due dates for Chapter 4 really start next week. I will have the homework for the first 3 sections up today. If you're comfortable with the Chapter 3 or done with the exam, you want to start looking at that homework. And what I should do here, all right, I'm going to try to figure out, I think I'll just end this. I'll just put the goat head picture on it. Reminds me of a Rolling Stone album cover. And then I'll just say, hey, if you have any questions, otherwise you can bow out of chat and I'll end the stream shortly. Be safe, be well.